At sea, ships use a compass to work out which way they're heading. For hundreds of years it's been the same sort of compass that you may well have used yourself when you've been out hiking in the country. A magnetic compass. A magnetic compass points towards the magnetic North Pole, which has an awkward habit of wandering around. Back in 1900 it was somewhere in northern Canada, whereas now it's much closer to the geographic North Pole. Anyway, the movement doesn't really matter because you can account for it by applying variation to magnetic compass bearings to turn them into true bearings. But there's an even bigger issue that we need to deal with. Ships are made of steel, which actually deflects the needle on a compass. To get around that, you employ a compass adjuster who will work out the right position for all the correctors, including those two iron spheres that you see on either side of every ship's compass. Anyway, magnetic compass correction would be an entire video on its own, so we won't go into too much detail today. The main takeaway that I want you to get is the magnetic compasses are deflected by anything metallic. We've just mentioned the ship's hull, but also things like cargo will have an impact, especially if it's metallic like iron ore. Fortunately, we do have an alternative to the magnetic compass. It's used not only by ships, but also by airliners, spaceships, and even your own bicycle. I'm talking, of course, about the gyroscope. A gyroscope is just a spinning disc mounted in a gimbal so that it's free to move. To start it spinning, you apply a force to the disc, making it rotate. You're building up its angular momentum. When something has angular momentum, we also say there's a torque present acting along its spin axis, so in this direction. A quick way of remembering it is using the right-hand rule. Curl your fingers in the direction of the force you applied, and your thumb tells you the direction of the torque. Anyway, enough of the physics, we now have a gyroscope happily spinning away. The interesting thing about a gyroscope is that it will keep pointing in the same direction unless you apply another force to it. Remember, we mounted it in a gimbal. You're free to rotate the gimbal, and the spin axis of the gyroscope will keep pointing the same way. Say, for example, you mounted the gyroscope in a spacecraft. As the spacecraft weaves and turns, the gyroscope is going to give you a consistent reference point. You can use it to work out which way the spacecraft is pointing. But does the same apply on Earth, say, in a ship? Well, actually it's not that easy. You see, the gyroscope doesn't maintain its axis in relation to the Earth, it maintains its axis in relation to the universe instead. I mean, gravity does have an effect, but we're not bothered about that for today. Take this example. If I start the gyroscope spinning at the equator, looking directly up, it will gradually turn as the Earth rotates. It is showing us the Earth's rotation. But what if, hypothetically, we try and stop it from turning in its gimbal? We're going to have to apply a force in this direction to resist its natural desire to turn. Remember, we're dealing with angular momentum and torques here, so things are not going to work as you expect. The force that you apply is actually a rotational force around this axis, trying to turn it in this direction. Remember, a rotational force with the right-hand rule is going to apply a torque. That torque is going to be in this direction. The new torque and the gyroscope's original torque interact with each other, making the gyroscope turn in this direction. This is gyroscopic precession. A gyroscope moves at right angles to the force you apply to it. All the while the Earth spins, you continue to resist that spin by applying a force, which creates a torque, slowly precessing the gyroscope. The only time it's going to stop is when the torque from the gyroscope and the torque that you apply are lined up. That will only happen when the gyroscope's spin axis is parallel to the Earth's spin axis, effectively when it points north. You've made a gyrocompass. It lines itself up with the Earth's rotational axis pointing north-south. Rather than needing you to apply a force to it, we just mount it in a gimbal that doesn't rotate completely freely. As the Earth spins, the damping effect forces the gyroscope to point north. Of course, real gyros have a little more complex damping than we've discussed because they never start on the equator pointing straight up, but you get the idea. You can damp a gyroscope and it will eventually settle in a minimum energy state pointing north. Of course, that's all well and good when it's sat in one spot, but remember, ships move. Okay, the speed of a ship is nothing compared to the Earth's rotational speed, but it can still have an effect. Imagine you have a ship with a gyrocompass pointing north, then your ship starts steaming north. As you steam north, following the curvature of the Earth, your gyro will naturally want to tilt upwards. The damping effect will create a force opposing the upward tilt, causing your gyro to precess to the west. This is steaming error. Of course, as we're following the laws of physics, you can mathematically calculate it based on your speed, your course and your latitude. If you give your gyrocompass a GPS feed, it can take care of this sort of error for you. In fact, the GPS feed can be used to correct for almost all errors on a gyrocompass. The main exemption is ballistic deflection if you're conducting lots of fast speed and course alterations, but on a ship you're going to struggle to do that anyway. So we now have a lovely spinning gyroscope pointing at the geographic North Pole. You would think things couldn't get any better than that, but actually they can. We can do away with the spinning lump of metal. Rather than a mechanical gyroscope, we can now use a fibre optic gyro instead. Fibre optic gyros rely on the Sagnac effect to detect rotation. Basically, you have a light source, a coil of fibre optic cable, and a detector. Fire a beam of light through a splitter and you can send two identical pulses through the coil in opposite directions. When they come out, you can detect them and see if they reappeared at the same time. If they did, there is no rotation. If there was rotation, say in this direction, you would expect that the light travelling in the opposite direction to the rotation will come out first. Work out the time between the light pulses and you can detect the rotation. Mount 3 of these detectors perpendicular to each other and you can detect rotation in 3 dimensions. A fibre optic gyro uses the Sagnac effect to detect the Earth's rotation and calculate which way is north. So, how does all this relate to your bicycle? Well, have you noticed how when you sit on a stationary bike you fall off, yet once the bike is moving it's incredibly stable? Your bike's wheels are acting like a gyroscope. The faster they spin, the more gyroscopic inertia they have and the more they will resist tilting. Gyroscopes really are amazing things and I hope you've enjoyed learning a little more about them today. Before we finished, I just wanted to thank my community over on Patreon. It was them that suggested we cover gyroscopes and it turned into a really fun video for us to make together. As the community grows, I hope to make these sort of videos more often where I literally let the entire community drive the content. If you want to take part next time, head over to Patreon to check it out. Otherwise, we publish here on YouTube on the last Friday of every month. Until next time, thank you for watching, and goodbye.